In 2026, silicon design has fractured into two entirely different computing philosophies. On one side, we have the versatile, general-purpose parallel processor. Architectures like NVIDIA's Vera Rubin platform rely on thousands of programmable CUDA cores designed to execute a vast array of mathematical operations. On the other side, we have the hyper-specialized application-specific integrated circuit, or ASIC. Google's Tensor Processing Unit family, now in its 8th generation, abandons general-purpose cores entirely in favor of dense, fixed-function hardware blocks built specifically for tensor algebra. This architectural split at the physical layer forces a radical shift in how software engineers actually build and deploy their code. The choice of silicon completely dictates the rules for compiler tooling, API availability, and memory management strategies. A machine learning engineer's day-to-day workflow now hinges entirely on whether they are compiling instructions for a highly programmable, dynamic core, or staging data to flow through a rigid, fixed-function array. Writing standardized, generalized code and expecting peak performance is a dead end. Optimization requires explicit knowledge of the target hardware's physical topology. To effectively deploy massive models in 2026, engineers must look beneath the API layer and understand the exact silicon execution models and physical limitations processing their data. Look at how these platforms are integrated at the node level. NVIDIA's Vera Rubin NVL72 rack-scale architecture connects 72 GPUs across a uniform all-to-all topology via NVLink, allowing any single GPU to communicate with any other with identical latency. Because they utilize standard PCIe interfaces, these GPUs slide into existing heterogeneous supercomputing environments. Traditional x86 or ARM CPUs and GPU accelerators dynamically share data and computational burdens on the fly. Google takes an entirely different approach, splitting their 8th-generation silicon into two distinct variants, the TPU-8T for massive throughput training and the 8i for ultra-low latency inference. This diagram illustrates the structural difference. Unlike the open web of NVIDIA's nodes on the left, Google's ecosystem is locked into a rigidly layered vertical stack on the right. TPUs connect via proprietary optical circuit switches and are hosted exclusively by custom Axion CPUs. The hardware, network, and host CPUs are inextricably linked. The Axion hosts handle all the complex sequential logic, restricting TPU execution strictly to the proprietary Google Cloud stack. This reveals a strict operational boundary. A TPU lacks the architectural flexibility to execute arbitrary, highly irregular branching logic natively. If a research pipeline requires high-fidelity physics simulations, dynamic pointer-based structures, or complex scientific solvers, engineers must default to GPUs. Fixed-function hardware will simply stall when forced to process non-matrix workloads. This animation demonstrates spatial reuse inside a Google Systolic array. When calculating dense tensor algebra, data flows smoothly through a tightly coupled 2D grid of processing elements, accumulating sums at each intersection. This continuous flow bypasses the von Neumann bottleneck because it doesn't need to write back to a central memory bank after every calculation. But watch what happens when the math changes. When a rigid square execution block attempts to process a highly irregular, tall and skinny matrix, massive sections of the grid are left completely empty and unutilized. Modern AI frameworks, particularly transformer layers, constantly generate these tall and skinny matrices. For NVIDIA GPUs, traditional standard libraries optimized for square matrices suffer severe performance degradation and hardware underutilization when handling these dimensions. The solution happens in software. Engineers developed the TSM2 algorithm for NVIDIA platforms, which specifically tailors memory access patterns for row major layouts to handle these irregular shapes. TSM2 forces hardware efficiency by logic repacking multiple distinct matrix fragments into a single unified tensor core operation. Google solves this geometry problem through the XLA compiler, which traces the computation graph in advance. It essentially looks into the future of the mathematical operations to calculate a precise memory schedule, explicitly pre-staging data from high-bandwidth memory into the SRAM. NVIDIA relies on tools like OpenAI Triton, using block-level programming instead of thread-level management. This abstraction lets developers focus on high-level data logic, while the compiler automatically handles low-level details like memory coalescing. Raw theoretical hardware speed means absolutely nothing if the software compiler cannot geometrically stage the data to match the exact physical dimensions of the chip. This alignment problem worsens with graph neural networks and recommendation models. These workloads operate on highly sparse data structures, presenting a worst-case mathematical scenario for dense matrix accelerators. This diagram shows what happens during complex scatter and gather operations on GPUs. The processing elements light up as active, creating a state of false high utilization, but they are functionally computing zero-value elements. Mitigating this wasted energy on an NVIDIA GPU requires aggressive software-side algorithmic reordering on the software side, utilizing libraries like QSparse to reorganize the data before the math occurs. The TPU architecture attacks sparsity with specialized silicon. A dedicated, smaller processing block intercepts the irregular data points, sorting them and feeding only dense, packed operations into the main array. This is Google's Sparse core. By physically offloading irregular embedding lookups to this subunit, the primary matrix unit processes dense operations continuously without stalling. However, dealing with sparse or irregular data outside of AI exposes a massive gap in ecosystem maturity. GPUs natively support legacy C++ and Vulkan compute shaders for arbitrary pointer-heavy data. TPUs, lacking native pointer arithmetic, face severe performance cliffs when forced out of their specialized domains. Achieving actual effective throughput requires precisely aligning the algorithm's density profile with the hardware's specific memory retrieval limits, not just chasing peak theoretical output. Even within specialized dense arrays, physical inefficiencies remain. In a traditional weight-stationary systolic array, data wavefront suffers synchronization penalties, stalling at the edge inside static buffers before proceeding block by block. To eliminate this static buffering, engineers developed the diagonal input permutated, or DIP, data flow architecture. Now, the input matrices feed into the processing grid diagonally, allowing entire rows to pass in parallel and flow seamlessly through the hardware. But this hardware upgrade comes with a strict software requirement. For the diagonal flow to work, the physical weight matrices must be transformed and rotated entirely in software prior to execution. By pre-computing the exact geometry of the data in software before it ever touches the chip, these systems yield massive improvements in computational throughput and physical energy efficiency at the cluster level. In 2026, the economics of AI infrastructure are dominated by inference, which hits a physical limit at the memory wall. The massive latency cost of retrieving the key value cache from external high-bandwidth memory. Google's TPU-8i addresses this physics problem by drastically expanding its on-chip SRAM, hosting massive caches directly on the die. This architectural decision pushes the chip closer to compute-in-memory principles, keeping the data exactly where the math occurs to slash latency. But that is hyperscale data center economics. When deploying inference at the edge on distributed, localized hardware, the on-chip memory is highly constrained, causing severe host memory bottlenecks. To survive these limitations, engineers use profiled model segmentation. The neural network itself is algorithmically sliced into distinct partitions, with each block assigned across a cluster of edge devices. Instead of forcing one chip to handle memory swapping, the layers are distributed sequentially to create a continuous processing pipeline. This distribution provides the necessary throughput to run massive networks on hardware that would otherwise be overwhelmed. Developers employ thread-safe queuing mechanisms to asynchronously pass the intermediate activation tensors from one device directly to the next. Eliminating host memory thrashing through intelligent, offline-profiled software pipelining is a critical mechanism for making massive models viable on highly limited edge hardware. Ultimately, the hardware dichotomy of 2026 centers on a multidimensional calculation of ecosystem commitment, algorithmic alignment, and total cost of ownership. Google's highly bifurcated TPU ASIC pods deliver optimized price-to-performance ratios specifically calibrated for massive-scale hyperscaler economics and repetitive agentic swarms. However, capturing that economic advantage requires developers to fully commit to the proprietary execution environment, conforming their models to the rigid constraints of the XLA compiler stack and dense operator fusion. NVIDIA maintains its dominance through programmatic versatility and a universally adopted software ecosystem. The mature CUDA platform and uniform NVLink infrastructure allow engineers to execute dynamic, pointer-heavy architectures alongside traditional computational fluid dynamics on the exact same silicon. Engineering leadership faces a definitive choice. They must decide whether their infrastructure requires the premium dynamic versatility of GPUs, or if they are willing to constrain their software architecture to capture the massive scale efficiency of fixed-function ASICs.